we will be working on example 2-1, and it says the screw I is subjected to two forces, F1 and F2. Determine the magnitude and direction of the resultant force. So we're basically just trying to find the force that is right here in the middle of these two forces. I think that's the middle, around there. So what I like doing first is finding this angle right here. And as you can tell, this problem already gave us these two angles. So what we could do is, this right here is a 90-degree angle. So these three angles have to equal 90 degrees. So if we were to do 90 minus 10 minus 15 degrees, that will give us 65. So we know that this angle right here is 65 degrees. From there, what I like doing is I like drawing a parallelogram to help me figure out some more things that I will be needing later in the future. So what we're going to do is we're going to take these two forces and we're going to draw them over here to the side. Right? So this it doesn't have to be exactly perfect, but it's just to help us like visualize things a bit better. Okay, so this is F2, this is F1. So to complete the parallelogram, what we're going to do is we're going to draw F2, and we're going to draw it right here on the other side. And then the same thing, we're going to take F1 and we're just going to draw it right here just to complete parallelogram. So we know that this is F1, this is F1, this is F2, and this is F2, right? Okay. From here, we know that this angle right here is the same as this angle right here. So we know that this angle is the 65-degree angle, and we know that these two angles are the same angles. So they're both 65. So we're just gonna come and write 65 on both angles. So from here, then, the only angle that is missing are these two angles. And once again, these two angles are going to be the same. So we're going to call these beta. So to find beta, we know that all of this, the whole parallelogram, has to equal 360 degrees. So we're going to put 360 equals, we have two 65 degrees, so 2 times 65 plus the two betas, right? So 2 times 65 is 130 plus 2 beta. And 360 minus 130 is 230. And then 230 divided by 2, that means each beta equals 115 degrees. So these angles right here, they both equal 115 degrees. Okay, now that we got that, what we're going to do is a formula that we're going to be using is the cosine law. And then from there, we just rearrange it just a bit. So in the end, from the cosine law, we are going to be using it like this. F of r, which is our resultant force that we're trying to find, is going to equal the square root of f of 1 squared plus f of 2 squared minus 2 times f of 1 times f of 2 times cosine beta. So here it's already given to us what f of 1 and f of 2 is. And from there we already found beta earlier on. So all that we're going to do is we're just going to simply plug it into the formula that we have right here. So we have f of 1 is equal to 100 squared plus f of 2 was 1/5 squared minus 2 times 100 times 150 times cosine of 115 degrees. So we're going to plug that into the calculator. And something that you want to make sure is to make sure that your calculator is in degrees and not radians. For this problem, we need our calculator in degrees. So once we put that into our calculator, we get that our resultant force is equal to 212.552 newtons, or 212.6 newtons, however you guys want to do it, if you guys want to round or not. So with that, we already determined the magnitude of the resultant force. But here it's also asking us to find the direction of the resultant force. So what we're going to do is right here, our little resultant force, we already found the magnitude of it, which was 212.6. Newtons. So now we're going to try to find the direction. And basically what that means is we're just trying to find the angle from like the x-axis going towards the resultant force. So from the x-axis, we are going counterclockwise until we hit that resultant force. So how can we do that? Well, this angle is basically just this angle plus this angle. So really the only thing we got to do is find this angle right here and then add it to the 15 degrees, and then we have our angle. So how are we going to find that angle? We're going to use again kind of like the parallelogram that we used earlier on. So again, we're going to take F2 and we're just going to put it on the other side. Oh, you don't want that. You want F1. That's not very pretty, but it's okay. And then from there, we're going to take F1 and we're going to move this up here too. Oh, wait. No. Let's go back. Sorry, you guys. That messed things up a little. Okay. Okay. Now let's retry this. We're just going to take this. We're going to move this to this side. Again, on the tip of F1. And then from there, we're going to take F1 and also just to finish off the parallelogram. So basically, our resultant force right here, it just basically moves all the way and it's supposed to touch the tip of where those two resultant forces meet. Why isn't it letting me? So basically, this resultant force is just to go from end to end. When we draw this parallelogram, it's just basically supposed to touch the tip. So again, we are trying to find this not that angle, but this angle right here. So what are we going to do? We're going to use the sine law. You're going to be using the sine law to find that. But first, we're just going to label. So F2 is this one and this one. So we're going to just label it F2 so we know this is F2, and then the other one is F1. Okay, so we're going to name this angle that we're trying to solve for theta. And we're just going to use the sine law. So for the sine law, we know that sine of theta goes over the opposite side. So the opposite side of theta is f of 2. We know that f of 2 is 150. So 150 newtons. Now we're going to be using the resultant force that we already found, which our resultant force was of, make it back down, 212.55 newtons, and which is this one right here. That's our resultant force. And the angle for that is the 115. So sine of 115. So from here, we're just going to solve for this. So we're trying to get theta by itself. So what we're going to do is we are going to multiply 150 to the other side just so we could get sine by itself. So sine of theta is equal to 150 newtons times sine of 115 all over 212.55 newtons. Again, we're going to input this into our calculator, and you want to make sure that your calculator is in degrees and not in radians. So we got sine of theta is equal to 0.6395. Okay, but we want theta. We don't want sine of theta. So what we're going to do is we're just going to move sine to the other side. So when we do that, we know that theta equals the sine inverse of 0.6395. So again, we're going to just input that into our calculator. 0.6395. So we got that theta is equal to 39.75 degrees, almost 40 degrees. But we're not done there, because again, theta was just this little angle right here. But we're trying to find the direction, which is the full angle right here. So the only thing we have to do now is just do theta plus this 15 degrees that was already given to us. So we're just going to do 15 degrees plus the theta that we found, so 39.75 degrees. So 39.75 degrees plus 15 will give us 54.75 degrees. If you were to round that, that's about 55 degrees. So with that, we determine the magnitude of the direction of the resulting force. So we determine the magnitude and the direction of the resulting force. So again, magnitude was the 212.552 newtons, and then the direction when how I like writing down my answer for the direction, just so like, because some people like finding it counterclockwise from the x-axis, and some people like finding it clockwise from the x-axis. So I like to specify which way I found it. So for us, or how I did it in this example, was this is our x-axis right here. So I found the angle going counterclockwise from the x-axis. So I always like specifying that. So we're basically just going to put here another direction was 54.75 degrees counterclockwise. And I like putting from positive x-axis. So this right here is our answer for the example 2-1. The screw eye is subjected to two forces, F1 and F2, and we were able to determine the magnitude and the direction of the resulting force.